Signs of life on an exoplanet? What's up with that? Welcome back to Orbit Insights. I'm Nathan Prather, and today we're discussing astronomers discovering strong evidence for one of the biomarkers of life on the planet K218B. Before we get into it, please subscribe if you are new to the channel. This will be the first part in a series that I'm planning to do, so make sure to subscribe for those future videos as well. I'm going to do, for this video, an overview of everything. Then the next one will be a deep dive, and I will also get a skeptic take as well. So this is the first time that we've seen an announcement of biomarkers indicating the possible existence of life on another planet. So it's not the detection of life, it's the detection of gases involved in life, as we at least currently know it. So, I mean, how do you detect life directly? We can't even really decide what life is. So, even if it's coming up with a way to detect it directly, it's very difficult, so we just kind of know the contaminants they release, really, into the atmosphere that we can detect. That's really all it is. And we're, like, we might say, hey, maybe, like, wait a minute, is the oxygen from a tree a contaminant? So, I mean, it's a waste product, really. So, in a way, so like photosynthesis, for instance, produces that if it's a tree, right? So, it might be something like that, but remember, this is 120 light years away, for context, right? So, this is a planet discovered by the Kepler mission. So, from the Kepler mission, really. This was discovered years ago. They weren't able to directly continue the mission. There were issues, we'll get into it. So, Kepler 2, so it had a failure, so it wasn't able to continue its original mission. So after 4 years, so it couldn't stare at the same stars anymore, but it could do a second phase of the mission, which is what ended up happening, where it looked at the ecliptic plane. So if you don't know what the ecliptic is, it's the imaginary line in space that the sun and all of the planets orbit along, really. So during that phase, it detected K218B. So just to get to the physics of the detection, so you've got a star, you've got the exoplanet orbiting the star. From the light from that star goes through the atmosphere and comes to you after it's been touched by the gaseous signatures in the atmosphere of the planet. So there are several different methods of exoplanet detection that astronomers use. I'll get to that in a different video, but there's like 4 different types. There's direct, transiting, there's different ones. So that'll be the topic for another video, but right now, so you need the Webb telescope to make this measurement. So you could do it with other telescopes potentially, like Hubble, for instance, has looked at this before with the wide ball camera. So that's an instrument, and in that case, but they weren't able to detect anything conclusively, so that's kind of that's the difference there. And we'll get into this later on, why this might not be conclusive either, but at least, well, at least you can see whether or not this is the signature. Not necessarily whether or not there is life there, but just that there's the possibility that there could be life there. So once JWST came around, everyone was very excited because this was one of the best targets. It's a planet with a nice puffy atmosphere around it. There's a bright star nearby. And it can be in the habitable zone too, potentially. So that's all good. So everyone knew this would always be a good planet. So they knew that, okay, so what does it mean for a planet to have a puffy atmosphere around it? So there's 3 ingredients of this. So low surface gravity, ideally. So this doesn't really have that, but it's not too bad. So you also want a warm planet. That's useful because it has up the gas. Also, obviously, if there was life, there would have to be at a certain temperature. So that's also important. But so you got a puffy atmosphere. You want also a light molecule gas because that can go higher in the gravitational well, and a larger atmosphere as well. We have a puffy atmosphere as it passes in front of the host star, so there's also more for us to see. And the list of biomarkers, last I checked, is pretty large. Even methane. So, also, for instance, we have lakes of methane on Saturn's moon, Hycean. Or Saturn's moon, Titan rather. It's what's referred to as a Hycean world. So, but no one's saying it's a place thriving with life. So, it's not just the existence of a chemical that can say, oh, this place is thriving with life. It could be it has that chemical, but there are other conditions. So it's not just the existence of the chemical, it's the conditions under which you expect to find that chemical and whether or not those other conditions exist. So the context is extremely important. So for instance, with this planet, there's some debate about what the planet really is. So there's this idea, is it an ocean world, which, as I said, is called a Hycean world. So this is a thin hydrogen atmosphere, and beneath it, you may potentially have an ocean. So there may be a surface of some kind. So if that's an important detail. Also, if this is really a Hycean world, it could potentially have methane. That, even having methane alone would kind of prove that there is life of some kind. I mean, we'll get into the fact, again, obviously, there's a difference between life and intelligent life, right? I mean, we're not going to find other humans, most likely not going to find aliens. I mean, the only reason there are other humans, right, is if we went there, right? So, but in words, we're not going to find other aliens or something like that. You would find some kind of microbial life, maybe something akin to plankton or some sort of bacteria. So I'm not quite sure what the numbers are, but basically you would expect it to be, there would be parts per million level of methane if there was no life, but this thing has a percent level of methane, so it has way more than it should. So when you have this photochemical, so what's the best way to get methane from life? Basically it's bacteria, some kind of bacteria, so I would guess, so basically, usually methane is always connected to life, really, so, because, like, for instance, humans, we have methane in our stomach, in our digestive tract, so that's why it's saying that there's methane. Basically, methane is produced by these microbes. Methane is also produced, I believe, whenever something dies. Like, if you look at, like, whenever, this is kind of a side note, but, like, whenever whales are bleached, the whales die, there's this huge release of methane gas, right? So that's why they're saying that. So methane is one of those byproducts. So if we already know that methane's there, but we're not quite sure of the environment, so then what else did they find? So they were putting stronger evidence for not only dimethyl sulfide, but also diamaldolfide. So these are two molecules which are on Earth, and they're only really produced by phytoplankton. So that's why I was saying that, I mean, this is really just a general rule, but if we discover any kind of other life, it's going to be some sort of phytoplankton microbial type organism, right? So that's why when they're looking for other life, it's primarily, oh, does this planet have, or planet or moon or whatever, have an ocean, for instance. So why do we even really care about the dimethyl sulfide? So if you have the methane as evidence, because it's not necessarily a Hycean world. So not everyone believes that. It might simply just be a mini Neptune, for instance. That's another option. So take Neptune, shrink it down by about a factor of 1.5 to 2 maybe, and maybe that's what this planet actually is. We don't know. And we'll get into later on in the video why there are so many questions around this. We'll be able to confirm it telescopically reading through the data. Hopefully that'll be confirmed in a couple of years, but it's still a little iffy. But maybe that's what this planet is. In that case, there would be this deep kind of ocean. There's no real surface, right? So you can just fall all the way down potentially to whatever core it has. So there's no real land. It's a water world, right? So there would be methane, ammonia, and these other gases being produced in the inside of this planet, in the interior, and then they would swell up through the convection currents and come up through the upper atmosphere where we could see them, detect them. So the fact that we see methane is consistent with the picture we would expect. So we would also expect to see these other things like ammonia present. The current data isn't actually good enough to distinguish ammonia and to distinguish, but that is possible. So we'll have to see. That could be one of these worlds. And the amount of ammonia it's just below our detection sensitivity. So it's not really a super Earth. So, but we don't really know what it is. And that's the other thing, is you have to really figure out what the planet is. And that once you figure that out, it really helps with categorizing a lot of the other things, because determining what type of planet it is determines what type of life it is. It could explain some of these other things, whether or not it's maybe just a new chemical process. We'll get into that later in this video. So that's an open question. It's about 2.5 times the radius of the Earth. Neptune's 4 times the radius of the Earth, so as I said, it could be a mini Neptune. So, and obviously Earth's 1, so it's somewhere in between, and we don't really know what this planet is. So we don't have anything in the solar system that really looks quite like it. At least that's the size. It does appear to be something of a mini Neptune, maybe. But we don't have a direct counterpart. Right, Neptune might be a counterpart, but it's not the right size. So the dimethyl sulfide's really interesting as a molecule. So interestingly, as a note, it's actually in truffles. So maybe you've eaten it. I don't know. So that's something that's really interesting. It's what this molecule is associated with. It's produced on Earth by phytoplankton and algae and things like that. So there are all these tiny microorganisms, right? So that's what makes it on Earth. So this concentration, it's hardly ever, it's like parts per billion concentration. So we don't know currently any other way this could be made naturally. And so that's the other thing that I'm going to get into actually right now, is if this is not the detection of life, it's at the very least the detection of a new type of chemical process. So even if it's not life, it's still really cool that we see this new chemical process, right? So that's awesome. So they've discovered these molecules on this planet, so we're thinking phytoplankton and ocean type environment, right? So it could be that, and they found much more of it at higher concentration on that planet than we have those chemicals on our planet. Much more, I mean 10,000 to 100 times 1,000 concentration. So we're talking about just driving, just a thriving biosphere with these microorganisms, if you believe the detection. And if you believe it, the only way to make that is something like phytoplankton, right? So if you're a skeptic, which again, I'm going to get into that whole argument in another video, but really that's just the overview. And overall it's really exciting. I mean, again, at the very least, this is a new chemical process, but that's all that they found. And that's my overview of what's going on with Kepler 218b. So share your thoughts down below. Subscribe for more parts in this series and more exciting videos. So share your thoughts down below. Subscribe today. And of course, as always, you can check out some more videos right now.